Assalamualaikum warahmatullahi wabarakatuh, and very good day. So for this part number 3, we will discuss about the flow work and also the energy of a flowing fluid. So as we discussed before in part number 2, I already mentioned that in energy balance equation for the open system, we have special terms that involve with flowing fluid, which is E mass in and also E mass out. So that term actually refer to the what we call workflow energy transfer. Workflow energy transfer. Okay, so now after this, we want to what I call derive we want to know what is the equation for E mass in and also E mass out. So before that, before we derive or before we obtain the equation for the E mass in and also E mass out, we need to know and also we need to learn about the flow work and also the energy of a flowing fluid. Okay, so this diagram shows a system that use a pump. So now we want to analyze the pump. Okay, so now try to zoom in the pump. So we try to get I call the inner part of the pump. So where we select the control volume, the boundary, and also the control volume. Okay, which is consists the main body of the pump. So this pump will have one inlet and also one outlet. Okay, so the outside of the control volume, we have certain amount or certain mass of fluid with certain parameters such as pressure, volume, and also mass. And we'll have a certain amount of distance because we want what we call push this fluid into the control volume. So in order to push this certain amount of mass of fluid enter the control volume, so we need to provide a force. So this force represented by the imaginary piston in this schematic diagram with cross-section area of A. So in order to to move a certain amount of fluid enter the control volume, so we need to provide certain value of force with certain distance L. So when we give a force, when the imaginary piston move, the second imaginary piston also will move. And this kind of energy or work we consider as flow work, where this flow work actually the energy or the work that we need to supply to a certain amount of fluid in order to make sure that the fluid enter the control volume. Okay, because we have force and also the distance, so the combination of force and distance will give us the value of work or energy, and this kind of energy we call flow work or flow energy. This diagram shows the condition before the fluid enter the control volume. So when we provide flow work to the fluid outside the control volume, okay, so the fluid will flow or move into the CV, control volume, due to the force that we provide at certain distance. Okay, so now in terms of equation, flow work will be equal to F multiplied by L, where as we know the formula for work when we provide force and also we have certain distance, so we will have the value or the formula for work. So for this case, this kind of work we call flow work, which is equal to F multiplied by length L. And due to the formula for F equal to PA, so we have flow work equal to PAL. Okay, A stand for cross-section area, L stand for distance, and P stand for pressure. And A multiplied by L actually equal to volume. So the final equation for flow work is equal to pressure multiplied by volume in kilojoule. However, if you want to consider what I call per unit mass, so we will have small letter W, flow equal to pressure multiplied by specific volume V in kilojoule per kg. Okay, so now we will have the total energy equation. So for closed system, the non-flowing fluid that represented by symbol E, we have learned this equation where E equal to U internal energy plus kinetic energy plus potential energy in kilojoule per kg. And if we elaborate the equation for KE and also PE, KE is equal to average velocity square divided by 2, and PE equal to gravitational acceleration multiplied by Z, the height of the certain point. Okay, so now we have second equation for total energy for non-flowing fluid, E equal to U plus V bar square divided by 2 plus GZ in kilojoule per kg. However, for flowing fluid, which is referred to the open system, the total energy for the flowing fluid that represented by theta, okay, equal to PV, pressure multiplied by specific volume, plus the total energy of the non-flowing fluid, E. And this PV refer to the flow work, which is referred to the equation of flow work that we discussed just now. Okay, so PV for flow work, and E is for the total energy for non-flowing fluid. Okay, so if we substitute what we call the equation into the theta equation, so we will have theta equal to PV plus U plus V bar square divided by 2 plus GZ in kilojoule per kg. And as we know, before this we have learned that PV plus U actually is the term for enthalpy, where we know that enthalpy equal to PV plus U. So we can substitute the enthalpy terms into the total energy of flowing fluid theta. So now we have final equation for the total energy of flowing fluid theta, where theta is equal to H enthalpy plus V bar square divided by 2 plus GZ in kilojoule per kg. So the total energy of flowing fluid equation will be the basis of the equation for E mass in and also E mass out in our energy balance equation for the open system. Okay, now we want to introduce, or we want to derive the energy transport or transfer by mass in terms of equation, okay, which is referred to the E mass equation. So energy balance equation that we have learned before, so we have E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equal to delta E system. So the term of E mass in minus E mass out actually refer to the energy transport or energy transfer by mass. Okay, so that the terminology or the term that describe, or the terminology that used to describe the symbol of E mass in minus E mass out. Okay, so if you refer to the previous control volume, when we discuss about the control volume for the pump, when we discuss about the flowing fluid, so we will have mass flow in and also the total energy in into the CV. So the rate of energy that enter the control volume will be m dot in multiplied by total energy in. So we will get the rate of energy flow into the control volume in kilowatt. Okay, so this the amount of energy that enter the control volume due to the flowing fluid refer as the amount of energy, where the symbol that we use is E mass, and the formula will be E mass equal to mass multiplied by total energy of flowing fluid theta in kilojoule, where theta equal to enthalpy plus the term for kinetic energy and also the term for potential energy. Okay, so if we elaborate by using a longer equation, so E mass equal to m multiplied by enthalpy plus kinetic energy terms and also potential energy terms in kilojoule. However, in terms of rate of energy, so E mass dot equal to m dot multiplied by total energy for the flowing fluid theta. So the unit will be kilowatt. Okay, so we have the same definition for theta. So E mass dot equal to m dot multiplied by h plus V average square divided by 2, the term for the kinetic energy, plus the term for potential energy in kilowatt. So this is the equation for E mass in and also E mass out. Example 4.4. Steam is leaving a 4-liter pressure cooker whose operating pressure is 150 kilopascal. It is observed that the amount of liquid in the cooker has decreased by 0.6 liter in 40 minutes after the steady operating conditions are established. And the cross-sectional area of the exit opening is 8 mm square. Determine A, the mass flow rate of the steam and the exit velocity. B, the total and flow energies of the steam per unit mass. And C, the rate of which energy leave the cooker by steam. Okay, so first we need to determine m dot, mass flow rate of the steam, and also the velocity of the steam. B, we want to know the total energy and also flow energy of the steam. And C, we need to determine the rate at which energy leave the cooker by steam. Okay, first we draw some sort of like schematic diagram. So at the beginning we have 4 liter of liquid, and the pressure inside the cooker is 150 kilopascal, and the opening of the pressure cooker exit in terms of cross-section area is 8 mm square. After 40 minutes, 0.6 liter of water will vaporize. Okay, and the vapor will release to the surrounding through the opening of the pressure cooker. Okay, so now this is the condition of the problem. So we need to solve to answer question A, B, and also C by using the information given by the example 4.4. Okay, now let us solve the question A, where we need to determine the mass flow rate of the steam and also the velocity of the steam that exit from the pressure cooker. Okay, so if you consider the information that given in the problem, so we know that in terms of the condition of the water inside the pressure cooker, part of the water is in liquid form and part of the water will be in vapor form or steam form. So the condition for pressure cooker in terms of water will be in saturation condition, where for fluid we refer as desaturated liquid, and for vapor or steam we refer as desaturated vapor. Okay, so from the information given in the question, the volume difference in terms of liquid will be equal to 0.6 L, where this volume actually evaporate from liquid to steam. And we know that 1 liter equal to 1 times 10 power of negative 3 meter cubic. First, we determine the mass of the liquid that change from liquid to what I call to the steam, and this mass of liquid actually same as the mass of steam produced during the process. So mass liquid equal to delta V liquid, which is referred to 0.6 liter, divided by Vf at 150 kilopascal. So because the equation involves liquid, the specific volume we need to refer to the value of Vf at 150 kilopascal. And this mass of liquid is considered as the mass of liquid water that evaporate during the process. Okay, from the saturated water table, based on pressure table, because we only have what I call the pressure value that given in the question. Okay, from the table, we find out the value for the 150 kilopascal, which is also equal to 0.15 megapascal. we need to find the value of Vf. So Vf based on the table at 150 kilopascal equal to 0.001053 meter cubic per kg, and substitute the value into the equation of mass of the liquid. So mass of the liquid equal to 0.6 times 10 power of negative 3 meter cubic divided by 0.001053 meter cubic per kg. So we'll get the value of mass of the liquid, which is equal to 0.570 kilogram. So this value actually same as the mass for the steam that produced during the process, where this mass liquid will change into mass of steam. So the amount of mass for liquid and also for the for the steam that produced equal to 0.570 kilogram. Okay, so in order to determine the mass flow rate of the steam that produced, so we use the relation where we know that mass of liquid water evaporated equal to mass of the steam exit. So mass flow rate of the steam, m steam dot, equal to m steam divided by delta T. So because the value is the same, so we just use m liquid divided by delta T, which is equal to 0.570 divided by 40 multiplied by 60, because we need to change from minute to second. Okay, we need to change minute to seconds, so we need to multiply with 60. So 40 times 60 equal to 2.37 times 10 power of negative 4 kilogram per second. So this is the value for the mass flow rate of the steam that exit from the pressure cooker. Okay, so I want to ask you one question. Okay, so I hope you try to get the answer. So for the equation for m liquid equal to delta V liquid divided by Vf at 150 kilopascal, why we not use because now we want to determine the mass of the steam. Okay, why we don't use the equation of mass steam equal to delta V steam divided by Vg? Why we not consider the delta V liquid same as the value of delta V steams? Okay, so this is my question that you need to try to get the answer. Try to think why the equation only refer to the m liquid equal to delta V liquid divided by Vf, not Vg and also V steam. Okay, I will let you to get the answer. Okay, second part of question A, where we need to determine what I call the velocity of the steam that exit from the pressure cooker. Okay, so we already calculate the mass of the liquid that evaporate during the process, which is equal to 0.570 kilogram, and we also calculate the what I call mass flow rate of the steam that come out from the pressure cooker, where m dot steam equal to 2.37 times 10 power of negative 4 kilogram per second. Okay, so now in order to get the velocity of the steam that exit from the pressure cooker, so we can manipulate the equation for m dot mass flow rate, where m mass flow rate for the steam equal to rho of the steam multiplied by A, cross section area, they are already given in the question, multiplied by the velocity of the average velocity of the steam, V bar steam. Okay, so now we don't have the value for the density of the steam. However, we can determine the density of the steam by using this formula, where density of the steam equal to mass of the steam divided by the volume of the steam, also equal to 1 divided by specific volume of the steam. So V steam, because the steam we consider as desaturated vapor, so the formula for rho steam, density of the steam, will be equal to 1 divided by Vg at 150 kilopascal. So the value of Vg we can determine from the saturated water table based on pressure table. Okay, so from the table we can get the value of Vg. Okay, so just rearrange the equation of mass flow rate of the steam. So you get the formula for the velocity of the steam, the average velocity of the steam, V steam bar equal to M steam dot divided by rho multiplied by A, equal to M steam dot multiplied by Vg at 150 kilopascal divided by A. Okay, so from the Vg at 150 kilopascal value that I obtained from the table, substitute into the equation for V bar steam. Okay, so 2.37 times 10 power of negative 4 kilogram per second multiplied by 1.1593 meter cube per kg. Okay, the value for Vg divided by the area of the outlet of the exit of the pressure cooker, which is equal to 8 millimeter square. So we need to change from millimeter square to meter square. So we need to divide with 8 times 10 power of negative 6 meter square. So the value will be V steam bar equal to 34.3 meter per second. Okay, question B. We need to determine the flow work and also the total energy involved with this problem. So the flow energy of steam, we can refer to the formula of enthalpy, where H equal to PV plus U. So the term for the PV actually refer to the flow work or flow energy. So the flow work or flow energy equal to PV equal to H minus U. Okay, so because now we consider the flow work for the steam, so we need to consider the value of enthalpy for saturated vapor and also the internal energy for the saturated vapor, which is equal to Hg at 150 kilopascal minus Ug at 150 kilopascal. So the value of Hg, Ug, we can determine from the saturated water table based on pressure. Okay, so from the table, Hg at 150 kilopascal equal to 2693.6 kJ per kg, and Ug at 150 kilopascal equal to 2519.7 kJ per kg. Okay, just substitute into the equation of flow work or flow energy. So flow work or flow energy equal to 2693.6 minus 2519.7 equal to 173.9 kJ per kg. Okay, next we want to determine the total energy of the steam. So we need to implement what I call the formula for the total energy for flowing fluid, where we have theta equal to H plus KE plus PE equal to H plus V bar square divided by 2 plus GZ. Okay, so we already determined the value of Hg because now involving steam, so the value of enthalpy we refer to the value of Hg. Okay, Hg. So Hg at 150 kilopascal plus V bar square divided by 2 plus GZ. Okay, equal to 2693.6 times 10 power of 3, okay, joule per kg. So we need to change from kilojoule to joule per kg because the term for kinetic energy will use joule. So we have the average velocity 34.3 square divided by 2. So we neglect the term for potential energy. So we'll get the total energy of steam equal to 2694.19 kilojoule per kg. Question C. The rate of steam energy. So we know that the rate of steam energy E mass dot will be equal to m dot steam multiplied by the total energy of steam theta. Okay, so we have 2.37 times 10 power of negative 4 kilogram per second multiplied by theta 2694.19 kilojoule per kg, will give us the value of E mass dot equal to 0.638 kilojoule per second. Okay, energy analysis of steady flow system. So like we consider a certain control volume where we have mass in and also mass out. So in the control volume, the mass of CV will be constant and the total energy for the control volume also will be constant, and the volume inside the control volume also will be constant. Okay, so for the energy analysis of the steady flow system, so we have two important equations. First, we have mass balance equation, so where we have total m dot in minus total m dot out equal to dmcv divided by dt or over dt. Okay, for steady flow system, so dmcv over dt will be 0. So we have remaining terms of m dot in, total m dot in will be equal to total m dot out. And the second important equation is the energy balance equation, where we have E dot in minus E dot out equal to dE system over dt. Okay, so the dE system over dt also will be 0 for the steady flow system, and the remaining term is E dot in equal to E dot out for the energy balance for the steady flow open system. Okay, so if we elaborate more for the energy balance equation, so we have E dot in minus E dot out equal to Q dot in minus Q dot out plus W dot in minus W dot out plus plus E dot mass in minus E dot mass out equal to 0 due to the steady flow process. Okay, so we just rearrange the equation, so we'll get Q dot in plus W dot in plus E dot mass in equal to Q dot out plus W dot out plus E dot mass out for the the general equation for energy balance equation for the steady flow process for the open system. So E mass out and also E mass in terms of formula equal to E mass dot mass equal to m dot multiplied by total energy of the flowing fluid theta. Okay, so if we substitute the equation, so we get Q in dot or Q dot in plus W dot in plus total m dot theta in equal to Q dot out plus W dot out plus total m dot theta out. Okay, so the theta refer to the what I call the full equation of the total energy for flowing fluid, where theta equal to enthalpy plus the term of kinetic energy and also plus the term for the potential energy. So this is the final energy balance equation for the open system and for the steady flow process. Okay, with the steady flow process, so we have Q dot in plus W dot in plus total what I call E mass in, which is referred to m dot multiplied by H plus V square divided by 2 plus GZ for in. Okay, we have total m dot multiplied by H plus kinetic energy term plus GZ in equal to Q dot out plus W dot out plus total out for m dot multiplied by H plus V bar square divided by 2, the term for kinetic energy, plus GZ, the term for potential energy. So this is the final general equation in terms of energy balance equation for the open system with steady flow process. Okay, now let's take an example in terms of energy analysis. We want to apply the energy balance equation for the open system, and we try to identify which terms that need to include in the equation and also which term that we need to exclude from the equation. Okay, so energy balance equation for steady flow process, we have the equation in terms of rate of energy balance equation in terms of unit kilojoule per second or kilowatt, or also we can use the unit of kilojoule per kg equation as shown in this slide. Okay, let's say we have a hot water tank with one inlet and one outlet. So the dotted red color line represent the control volume. So we have electric heating element where we need to supply WE, electrical work, rate of electrical work, WE dot, and we have cold water enter the tank, that represented by in terms of mass flow rate m dot 1, and the hot water come out from the tank due to the presence of the electric heating element, where the rate will be m dot 2, and the value of m dot 2 equal to m dot 1 based on the conservation principle of mass. And for this system, we consider heat loss to surrounding, that represented by Q dot loss. And now we try to simplify the energy balance equation based on this specific case or specific system. So we need to identify which energy that cross the boundary, which energy transfer in, and which energy transfer out. And also we need to identify which energy term that is not related to the system. Okay, so we just write the full equation for the energy balance equation for the open system. So for this system, we neglect the term for kinetic energy, the term for potential energy for both inlet and also outlet. So by referring to this schematic diagram, we will have no Q in dot, no Q in dot, no W out dot. Okay, so the remaining terms will involve in the equation. So the final equation will be W in dot or W dot in plus total M dot H in equal to Q dot out plus total M dot H out. Okay, so now try to be specific in terms of equation by referring to the symbol of the energy that used in this schematic diagram. So we have the final equation for this specific system. So we have W dot E, electrical power, plus M dot 1 multiplied by H1 equal to Q dot loss due to the heat loss, plus M dot 2 multiplied by H2. Okay, just rearrange the equation. So we'll get W dot E minus Q dot loss equal to M dot multiplied by H2 minus H1. Okay, so this is how we implement the energy balance equation for the open system based on the specific system or specific schematic diagram. Okay, so I have one question, important question. I want to know why we neglect the kinetic energy and also potential energy terms in the equation. Okay, because if you look at the schematic diagram, at the inlet we have mass flow rate. For sure, the fluid will have certain velocity, V1 for example, and also same goes to the mass flow rate at the outlet. For sure, we also have the fluid at the outlet also will have velocity. But now we neglect the term for kinetic energy, because the kinetic energy also will involve with the fluid velocity at the inlet and also at the outlet. Okay, same goes to the height of the inlet and also the height of the outlet. So if you look, we will have certain value of height for the inlet position and also for the outlet position. So why in this equation or in this analysis we neglect the term for kinetic energy and also the term for potential energy? Okay, so I want you to try to give me the answer during the class. Okay, try to get the answer. Think a little bit and try to get the answer. Why this happen? Why we neglect the kinetic energy terms and also the potential energy term in our energy analysis for the open system. Okay, so the second example, okay, we implement the same approach where we have energy balance equation, the same energy balance equation, but now we have different system. We have a pipe, and the dotted red line represent the control volume, and we have mass flow rate at the inlet M1 dot, and we have electric heating element inside the pipe, and we need to provide electrical work or electrical power in order to provide heat. And also we have some sort like a fan. So for this case, we will have what I call the rate of shaft work, W dot shaft. But for this case, the case will be the flow inside the pipe will cause rotational movement of the fan of the shaft. And we have mass flow rate at the outlet of the pipe, m.2, also equal to m.1. Okay, so now we want to determine the energy balance equation for this case. So we need to determine which energy that cross the boundary, which one energy transfer in, which one energy transfer out, and which energy not related to the in the equation. So this is the what I call the full equation for the steady flow system, energy balance equation for the open system with a steady flow process. Okay, so we neglect kinetic energy terms, potential energy terms, so we don't have any Q in dot, Q out dot. So the remaining terms for the equation will be W dot in plus total M dot H in equal to W dot out plus total M dot H out. So make it more specific based on the parameter or symbol that you use in the schematic diagram. So we'll have W dot E, electrical rate of electrical work, plus M1 dot multiplied by H1 equal to the rate of shaft work, W dot shaft SH plus M dot 2 multiplied by H2. So rearrange the equation. So we have the final energy balance equation for this specific system, where W dot E minus W dot SH, rate of shaft work, equal to M dot multiplied by H2 minus H1. Okay, so this is how we implement the energy balance equation to the specific system. Okay, now by referring to the schematic diagram, so this schematic diagram we have some modification compared to the previous example. So I want you to write down or to get the specific energy balance equation for this system, where if you look at the system, we have one inlet, we have two outlets, and in the system we have the electric heating element to provide Q dot E, and also we have Q dot loss to surrounding, heat loss to surrounding. And in the pipe also will have shaft work represented by the what I call the equipment or the device that have a fan. We have mass in M1 dot, mass out M2 dot, and also M3 dot. So try to get the complete energy balance equation for this system. Okay, so the energy balance equation that you need to use is the energy balance equation for the open system with steady flow process. Okay, you need to use this equation and try to simplify the equation.